right, so the talk we're doing, Dockerizing Cassandra on Azure. I'm Richard Banks. This is Adam Zegelin over here from Instacluster. I'm not, I'm from Redify, just in case that wasn't clear, which it wasn't. All right, and the way we're going to do this, I'm going to talk through Docker and where Docker fits into the picture, the principles behind it a little bit, and then I'm going to throw over to Adam, who's going to show you all the awesomeness, and I'm just kind of here as the pretty face. So you get what you get towards the end of a conference, unfortunately. All right, so setting the scene. That joke fell flat. So setting the scene, Docker, woohoo! And now, out of curiosity, who's been to sessions talking containers or Docker or anything like that so far? So a few of you, who was in my session yesterday? Okay, sorry about that. Who was in the Windows container session? Yep, okay, a few of you as well. And I think there was, Mahesh did a microservices talk yesterday as well. So there's been a few things around Docker and microservices and containers and the architectural concept. So you've probably picked up a fair bit of this. But what I want to do is just talk through some of the principles behind it. So containers, huh? Who knew? It's literally this metaphor applied to software. When we're talking software containers, we're talking this. So the idea with a container is that I can take anything I've got and I shove it into my box, and then I put my box on a ship or a truck and send it to wherever I need to. And the thing that hosts that container, the vessel, it doesn't really care what's inside the container. It just does its magic. And apparently there's a haka or something going on next door. I don't know what's going on there, which will come through great on the recording. So anyway, we've got these containers. Now, containers themselves, before we had them, how do we used to load vessels? It's kind of, why am I talking about this? It's awesome. So before containers, we had these cargo nets, and we'd load our stuff up in the cargo nets, and we'd have the stevedores lift them up and drop them on the ship and try and figure out how to balance out a ship as best they can. And this process was a little bit error-prone. It didn't really pack things well inside a vessel. We definitely didn't make good use of the space. It was a manual process, expensive, time-consuming, and so forth. Then someone came along and thought about, ooh, what if I could modularize my storage? And then I simply take my modules and do that. Anyone know roughly when this occurred? No one's in logistics at all? Okay. So this happened back in 56-ish. And at that point, loading a vessel cost $5.65 a ton, with all the manual handling and the breakage and insurance and all that sort of stuff. Containers came along, Sealand shipping lines started doing their thing and reduced the cost down to 16 cents a ton. Massive saving. The reason it works is because of standardization. Because now, in terms of loading a vessel, I don't have to think about cargo nets and balancing drums of oil versus fish versus long, sharp javelin poles or anything like that. We'll just carry on. And instead, it's literally take the container, move it in. Where that applies in terms of software is kind of interesting. And as you can see, containers have overtaken the world. You don't see anyone manually loading vessels anymore. It just doesn't happen because the cost isn't worth it. And we're going to see this happen in terms of software as well and applications. How extensive it gets, I don't know if it will get like that, but it will definitely improve. So consider for us a virtual machine. We start with a VM, right? Traditionally, what do we do with that VM? We load a big fat old application onto it. Fantastic, and we figure out how to pack it into our ship, so to speak. And we put that image in there, and then everything's running great until what happens? Server load goes up. People start actually using our application. Gasp. And then we start to struggle, and we think, oh, now we need to scale this thing, right? So how do we scale? Well, we simply buy bigger hardware, right? No. Well, some of us do. It's the short-term solution, buy a bigger ship. But our two options are generally scale up and scale out. Scale up works great as long as your scale only wants to get to 8 cores or 16 cores or whatever it is, and you like paying for expensive hardware, or you buy lots of cheap hardware and you scale out, which gives you much more scale, and that's obviously where the cloud is these days. And as I scale out, I take these VMs and I drop my application into it each time, and I might have to adjust stuff to deal with things like load balancing and so forth. And there's a little bit more complexity around this space in terms of trying to manage it. But if I look at that, I'm actually wasting capacity. I don't actually get to optimize the use of my resources or fill my ship properly as best I can. Because what if my application is actually consisting of a web component and an API component? It's pretty common, for example. And the web part's not actually where our load is. If we analyze our solution, what we see is it's actually the API where our processing demands are. And so what we're doing is we're duplicating the web across the other two machines for no real reason. Instead, what we really want is that. This is where containers start to help. So if instead I take the web section of my big application and the API section of my big application, I drop them in as Docker containers, for example, then what can I do? I can create an image out of that. Now, an image, for those who aren't aware, in Docker land, is effectively a read-only view of what my application will be. It's immutable infrastructure, effectively. It doesn't change. If I start up an image and I get a running container and I change information in that container, it doesn't affect the base image, okay? So it's like a template. I start that up, I create containers. I might create 2 web containers and 3 API containers. Then I simply drop those into my host, and now I can pack them more densely because I don't have as much overhead each time. And the container footprint is quite small. I don't have to run up an entire VM to run these things. I can simply run a base VM and then run these Docker containerized images inside that VM. Make sense? So I get more density. When we're talking about cloud and scale and everything else, application density and compute density is critical because that's where our cost comes. Every time you spin up a new piece of hardware, you've got extra power, extra heat to deal with, extra space to deal with, all those sort of things. And you have that extra complexity. We don't want to have that. So, do you want that picture back? Whoever was taking a photo, you're all good? Cool. So think of containers a bit like lightweight VMs. Virtualization abstracted away the hardware level. Yep. So we have virtual machines, we abstract away the physical hardware, and we just deal with this well-known set of hardware. Containers abstract away the operating system. You have a base OS that effectively virtualizes the OS, regardless of what the OS is doing underneath in terms of patch levels and things like that. We have a well-known operating system that we work with, and it proxies calls to the base OS. So it's virtualizing the OS versus the hardware. So traditional VMs, as we talked about, we've got our host, we have our host OS, and then a virtual machine, it duplicates that information. It's extra space, extra capacity, extra resources that we don't need to duplicate. Instead, what we do is we share the host across all the containers, and we only have to duplicate the minimum needed in each container. So again, we're able to pack more in. So whereas we might have only been able to support 3 VMs, we could now support maybe 6 containers or something like that, or even more. So we've got much more density, and that's really what we're after. In terms of these 2 slides, I'm not going to dwell on them too much. Have a look through later on. But the key thing to note is that containers are fast. How long does it take to spin up a VM? Anyone know, roughly? 5 minutes, if you're lucky, depending on what you've got in there. A container should spin up in around 400-ish milliseconds in general, depending on what you've got in there. So you can spin these things up rapidly, tear them down rapidly, and it changes the way you think about your application and how you actually deploy things and how you manage workloads and all sorts of stuff. And if you want flexible scale, I don't have to worry about the time it takes to start and tear down a VM. I can literally start a container up for extra compute load. As soon as my compute load drops off, I can get rid of my container. And I'm not having to worry about too much capacity information in terms of virtualized hardware. Containerized apps, in terms of where things are heading, Linux is obviously where the maturity is at this stage, but containerized apps will run anywhere that the containers themselves run. The trick is here just to be aware that if you build an app aiming at a Linux host or a Linux container, it only runs on Linux host because it's virtualizing the OS, remember? You can't run that thing on a Windows host, okay? So Windows Server 2016 isn't going to run Linux containers. Similarly, Core OS, Ubuntu, whatever else, is not going to run a Windows container because the OS virtualization just doesn't map across. You know, different file systems, different process management, all those sort of things, it just doesn't apply. All right, From a operational perspective, this slide's been shown a fair bit, but basically containers change the way you think about the development, test, and deployment lifecycle. So we start off with the devs who build applications. They build them with containers on their own machine. They'll bring down containers, they'll work with them locally, they'll update their code, they'll make sure that runs in a container, it's all good, and they'll check that code into source control. Source control will do a build, it will create a good image so that we're not actually deploying from a dev machine. And we push that into our central repository, which could be something like Artifactory or ProGet, MyGet, one of those sort of systems that handle Docker images. Ops team picks those up and then deploys them to the appropriate environment, whether it's a UAT environment, staging, production, whatever it is. And we're effectively promoting containers through these environments. It's the same thing every single environment. So if the ops guys or infrastructure somewhere notices a problem in a container in production, in order for a dev to fix that, they simply look at the container. It's the same container. They can run that on their own machine and see what the difference is. So we don't have works on my machine problems, or we shouldn't have works on my machine problems anymore, because we can literally take those containers and see what they're doing. If there's a problem, they then fix it, update the container image, or actually create a new container image. We don't update, we only create new, and then replace the container in production. So traditional approaches for application is we upgrade. We take the application, we do an upgrade script, a cycle, whatever else. We don't do that with containers. We literally take the old container, move it out, drop a new container in. It's a replace, not an upgrade cycle. Changes the way you think, again, about how you manage your applications in production. In terms of Docker itself, there's a large community, especially in the Linux space. It's been around for a few years now. We see all sorts of things happening in that space: Redis, Ubuntu, Mongo, all these images and official repositories out there. So if you wanted to spin up a Redis environment in your own system, you could basically spin up a Linux host, grab the Redis containers and drop them on your machines, and you're up and running. Almost zero configuration. Just open up and map some ports and you're good to go. Cassandra itself is in there, which is cool. We're going to talk about that. When I say we, I mean Adam. No pressure, dude. And where Microsoft's going with this, just so you're aware, is they're treating this as working with Docker. So they'll run Windows containers or Linux containers, whatever you like. It doesn't really matter. Microsoft's effort with Docker is not to create a Docker MS or an MS Docker or anything like that. It is literally they're working with the Docker team so that they support Windows containers. It's a joint effort, it's collaborative, it's open source. You can jump onto GitHub and see the code. It's very cool. And then you can run those containers wherever you can run Docker hosts. So, your own environments, your own desktops, Azure machines, wherever else it happens to be. And there's a bit more there. I'm going to skip that one because I want to jump over to the meat of this particular talk, which is Instacluster. So I'm going to hand over to Adam now, who's going to wow you with his awesomeness.
Cool.
We'll
Thanks,
go
Richard.
from there.
It was a fantastic introduction to Docker. I think we all enjoyed that. So how does this thing work? Press the big button, I guess.
The one to the right.
One to the right, yeah.
Yes.
Cool. So good day. As Richard said, my name's Adam. I'm the technical co-founder of a company called Instacluster. And we do managed Cassandra in the cloud. So just a little bit of a background about what Instacluster does. We provide a self-service dashboard for our customers that they can go in and they can create and manage and monitor clusters of Cassandra nodes. And then, we provide the 24/7, 365 support, on-call engineers, we have an uptime guarantee, all that kind of stuff. And so the whole idea of this thing is so that you guys, you can focus on writing your applications, and we focus on running the infrastructure behind that, the Cassandra. Instacluster itself actually grew from a need for a project that myself and my co-founder, Ben Bromhead, were working on before we started Instacluster, where we were writing an app. We picked on Cassandra as the data store mechanism behind it, and went out and looked on the market for somebody would host it for us. And you know, we didn't want to host it ourselves. You know, at that time, Cassandra was it was like 0.8 kind of version thing, so it hadn't even hit like version 1 yet. So there was a few rough edges around the sides, and you know, people sort of said, look, you know, if you want to run this yourself, you're going to need like a dedicated ops guy, or probably even a team of people to be able to kind of run this thing reliably. You know, it'll probably, everybody's experience with it was that you know, it'd run fine for a while, then it'd possibly catch on fire a little bit, and nobody really knew how to put things out. So, you know, we were kind of a little bit hesitant to sort of pick this if we couldn't, pick Cassandra as the technology if we couldn't find somebody to host it for us. So we went looking, and we didn't find anybody out there, and kind of had this, you know, what if moment. You know, maybe we try doing something completely different from the original idea. And, you know, we talked about it with our sort of like original investors and stuff like that, and they all thought that it was actually a fantastic idea, that we should, you know, turn the ship in a completely different direction and go after something else entirely, which was hosting and managing Cassandra. So here we are 2.5 years later. I consider we're probably the best Cassandra hosting company in the world, if not the only one. I'm not sure if there are competitors out there. They seem to pop up on the horizon a little bit and then disappear. And so, you know, we're doing pretty well. We've got about, it's like 450 Cassandra nodes under management across about 40 clusters or so. So one cluster per kind of customer sort of thing, with a total of probably, you know, it's in the hundreds of terabytes worth of data under management on the system. So just a little bit of background about, you know, what is Cassandra? I mean, I mentioned the name and everybody's probably going, you know, what is this? They've never heard of it before. So Cassandra is a open source NoSQL data store. It's designed for high performance, extremely high throughput applications. And it has a lot of good qualities about it. It's fault tolerant. So your data is actually replicated amongst multiple nodes, and that's actually tunable. You can specify how many copies you want. It's scalable, so you can add nodes as the demand for you know, the kind of throughput increases. So your application grows, and you want more you know, read and write operations the database provides you. And the cool thing about that scalability is that it's actually linear. So you add more nodes, and you know, so if you double the capacity, it doubles the performance, which is, you know, pretty awesome. It's decentralized, meaning that you know, if a node goes down, the rest of the system keeps on running. It doesn't even notice, you know, which is fantastic from a, you know, a day-to-day kind of operations perspective as well, because it means that, you know, we can do maintenance on a node, and okay, we inform our customers that we're going to do this, but they don't notice that, you know, a node has gone down. Their application just keeps on running, and then when it comes back online, it just, you know, rejoins the cluster, and everything keeps on working as if nothing happened. It's multi-data center capable as well, so you can do replications across regions, and Cassandra sort of understands that concept, so it has this built-in idea of what is a data center and how data should be replicated between those. You know, it doesn't insist that clients end up connecting to a data center that's on the other side of the world and you get horrible latency and things. Everything's all aware of that topology. And it has, it's got this thing called tunable consistency as well. So you can kind of, depending on the topology of your cluster and, you know, how reliable and performant, so they're kind of all tunable things that you can adjust. And, you know, you can do things from the perspective of, you know, writes will never fail. So it's like you throw it, and if the whole cluster's down, the client's gone, oh, okay, I've written to something. I don't know if there's actually anything there, but it's all good. All the way up to, you've got to wait for a confirmation from every node in the cluster saying, yes, we've written that data to disk. It's all good. Give me some more, kind of thing. And, you know, there's a thing in the middle as well. So like I was saying, you know, Cassandra, it scales. So, you know, this is a pretty simplified example here, but, you know, imagine if you've got a cluster of 3 nodes and you add 3 more, it doubles your capacity up to 6,000 hops per second. You add another 3 more nodes and you've got 9,000. We see people use Cassandra for a variety of use cases. You know, everything from internet advertising, you know, recording every click. And that's what I mean by like high throughput applications. You know, you can imagine some of these advertising platforms, they get millions of impressions a day. And when you work that out, that's, you know, thousands, if not tens of thousands of clicks per second, and they want to record information about every single one of those clicks. That's a lot of data to be storing into the database at such a speed as well, so Cassandra handles that. Other cases we've seen is, Internet of Things applications. We've got all these smart devices collecting information from all these sensors, telemetry. We ourselves actually record data about every node we run in production and store that in Cassandra, so then we can do analytics and processing over that data. And yeah, online games. Anything you could think of, probably, in one case or another, could be run on top of Cassandra. It's also, it's been battle tested by a bunch of people. Microsoft uses it, Netflix uses it, eBay, Apple. They're all names that everybody's heard of, and they're kind of running this in production as a stable data storage platform. So we think it's a really great piece of technology, and we're just starting to see more and more people use this. So we want to provide the best kind of service for hosting Cassandra in the cloud. How do we do that? And why is running Cassandra in the cloud such a great idea? So, of course, some of these things are just standard cloud kind of concepts, but you pay for what you use in the cloud. So if you need more servers, you pay for it. If you don't need those servers, you turn them off. You're no longer paying for them. Hardware provisioning is no longer really a concern. You don't have to wait a month for the servers to show up and then some guy to install it in the rack and then hook it all up. It takes ages for it to come online. You can react to the changes in your capacity requirements quite quickly. And because Cassandra is this clustered thing, it facilitates that as well. You add more nodes, it scales with that. So that's why we feel that Cassandra is a great fit for hosting it in the cloud, because it blends quite well together with these technologies. So where have we come from? So like I said, we've been around for 2.5 years. We didn't actually use Docker right back at the very beginning. We did something fairly, I guess, classic. What we did was we ran Ubuntu, and that was just a standard Ubuntu image that we'd built, and we then customized it with a bunch of stuff that we needed. So there's this thing called Cloud Init, which is stuff that runs on startup of the operating system. We'd modified this to these scripts to do things like RAID the disks together if there's multiple disks on the machine, so you get better performance. Fetch the configuration for Cassandra from our central server somewhere, so that we know we can tailor the configuration to what the customer needs. And Cassandra itself was actually just installed with the classic apt-get install Cassandra, or if it was the DataStax Enterprise version, which is the commercial version of Cassandra, we'd install it using their software repositories as well. If we wanted to upgrade the version of Cassandra that we were running on this machine, we just did an in-place upgrade. You just run apt-get install again, it'd install the newer version of the package. And you can do package pinning and all that kind of thing, but it worked, but it was kind of painful. And I'll go into a little bit more when I start talking about Docker, about why it was painful and why we moved away from this model, because it just, like I said, it worked, but we wanted something better. So what does our software stack look like these days? We run CoreOS as the operating system of choice for all our Cassandra nodes. As a matter of fact, even our central management servers and stuff all run CoreOS. CoreOS is a lightweight container runtime operating system. It pretty much just runs Docker. There's not much else running on it. We then picked Docker as the containerization engine. Of course, it was kind of the one that it was starting to make a name for itself. Everybody had heard of it by that point. There was enough documentation and community support around things that we weren't really kind of diving into this on our own, kind of uncharted territory kind of thing. CoreOS also runs a couple of more modern Linux technologies, such as systemd and journald. I know these things get a little bit of hate sometimes, but we use them and we think they're fantastic. And then you've also got available on the machine this thing called dbus, which is basically a inter-process system that you can control systemd and stuff like that via IPC. So CoreOS, like I said, it was one of the first Docker operating systems. It's extremely small and minimalist. I think it comes under like 300 megabytes or something for the base OS image. It might even be smaller than that. But why is it so small? It doesn't actually have that much stuff in it. There's not much userland utilities available. It doesn't even have man pages installed, which can be a little bit frustrating at times, but that's how you save space, right? Is you just don't install all this extra stuff. And like I said, it runs systemd. And Ubuntu, when we were using it, they were in the middle of this transition away from the kind of very classic sysv init system to Upstart, which was their own kind of homebrew init system that had a few kind of rough edges and stuff, and we're a little bit hesitant to change over to that system. Whereas systemd seemed to be supported, it's written by Red Hat, and so they've kind of got a bit of commercial support, all that kind of thing behind it. Paired with systemd, you've got journald, which is basically a replacement for syslog and a bunch of logging frameworks. And then, like I said, this is all kind of controllable via this thing called dbus. CoreOS also, by the time we started using it, was in use by a number of larger players in the space. Again, names that you've probably heard of, people like Rackspace and PlayStation, and now us as well. And they've also received some recent funding from Google Ventures, which kind of, we feel, means that they will hopefully be around for a while and keep providing this nice piece of technology. Something else that CoreOS does, which is quite nice, is they're responsible for building the images for most of the popular cloud providers out there. So that's one less thing that we had to deal with. Like I said, originally we were building custom Ubuntu images. We'd have to build these images every time we wanted to do a new version of Cassandra, and the process for doing that is different for every provider out there. I know there's tools that kind of facilitate doing multi-provider builds and stuff, but they've all got their own set of quirks and problems as well. So by us using this off-the-shelf image that we don't have to customize at all, it's their problem. They're the ones that build this thing for us, and we just use it, which is great. It's one less thing. And the other really cool thing it's got is this. It does in-place upgrades, but you can then roll back those upgrades instead of failures. So you think, okay, Docker's great because it containerizes all your applications, but what about the system itself? You want a new version of the kernel. You want a new version of Docker running on the machine. How do you handle the upgrades of these things? Because then you're kind of back to square one. You've got to install this software from somewhere. CoreOS does it where they have, going into the details a little bit, they've got like 2 petitions that they format the disk with, and one of those is marked as active at any one time. And then updates are downloaded and installed. It's completely sort of immutable, installed onto the second inactive petition. It then swaps the active flag over, and then when you restart the machine, it then boots from the now new active petition with the new updates installed on it. But if it all goes pear-shaped, you can then switch back to the previous petition, which, and then everything should just continue running as if the upgrade never happened at all, which is really cool. It's based off something that I think Chrome OS uses for their kind of update strategy, and it's something that you're starting to see for a lot of these immutable operating systems is a sort of some in-place update with rollback kind of feature. So this is really cool. It saved our ass a couple of times. So, Docker. What is it? Well, like Richard said, it's a container runtime. It also provides a standardized image distribution and hosting kind of framework. So it has the ability to pull images from places. The project includes code to host those images. And then there's also the whole ecosystem around it. So plenty of people build Docker containers for well-known pieces of software, so you can just go and get those off the shelf and plug them into your Docker runtime, and you've suddenly got whatever piece of software you're after. But the great thing about it is it gives you immutable images, which is fantastic. That's like the coolest thing of the whole thing. It means that you never change anything running in the image. If you want something different, you make a new image, and you can keep track of those. And just like the whole rollback thing with CoreOS, if something goes wrong with the new one, you just stop using it and use the old one that you've still got around. So you've kind of got this very easy migration path for your upgrades of software. The other cool thing is that the images that you build in your development environment, so as you're testing these images and trying to get the software to be installed and work correctly, once you've got those working, you can put them in your test environment and verify it more in a sort of production thing. And then you can even move those into your production environment, and therefore your customers are actually using the exact same images that you built on your development machine. And like you said before, if something goes wrong in production, you can then bring that image and run it back on your development machine and kind of debug the process and figure out what's going wrong. So everything's nice and consistent across all these environments, which that's really cool. It also, because these things are like sandboxes, all the components running inside them, they're isolated. So it lets you do things that were perhaps a little bit difficult with traditional apt-get kind of installs, where if software A requires version 1 of a particular library and software B requires version 2, and suddenly they're kind of all based on one package. And so you install software B, software A gets uninstalled because there's a conflict, and how do you deal with this and all that sort of stuff? Docker just gets rid of that completely, because every container can have its own set of installed software, which is completely independent of every other container. So you can run different JVMs, different library versions of OpenSSL. That's a good one that always has problems. And we do this DataStax Enterprise, which is the commercial version of Cassandra, really likes to use the Oracle runtime of Java, whereas we use the OpenJDK for a bunch of other reasons. But you can't really install those two on the same machine, but you can install them in two separate containers and run them at the same time, which is really useful. We containerize everything across all our systems, so not only Cassandra, but all our internal services, our website, our dashboard, that's all containerized. All the systems that handle provisioning of Cassandra clusters, that's all containerized. And then all the applications that run on the nodes to do all the monitoring and reconfiguration at runtime, all that kind of stuff, it's all containerized. Why do we do this? It means that the runtime environment is well understood, but also the build and deploy process for building these, all these applications is the same. It helps that we write everything in Java. Cassandra is also a Java application, so you kind of got everything's Java based, but you've kind of got all these separate containers, but the build process for them is identical. We do something a little bit old school. We actually kick off the build process for making Docker images via makefiles. So we've kind of got like a target for each image that we're interested in, and then there's an all target which will go through and build everything that you're interested in. And then you can also push stuff via that mechanism as well. So I won't go into too much detail about that. If you want to ask me some questions afterwards, I'll be happy to answer them. But it's very useful for improving our build process as well. Our kind of container, I don't know if anyone's really played with Docker too much, but Docker has this thing where images can depend on each other, which is quite useful because it means that you're not in every image including the same stuff. You kind of, you can once you've installed one image, kind of like a base image, you can then install other components. It doesn't have to re-download all that stuff. They kind of share this common underlying base. And so this diagram here shows that kind of how we build our images. We build everything on top of Debian, and then we've kind of built a common image that we ourselves use, which includes kind of all the stuff that you really need to make Debian a little bit more useful and what a lot of applications require. So that's things like, Python's very useful for running little scripts in the background, OpenSSL, curl, all these utilities, bzip is another one there, if you need to extract data, all that kind of stuff. And all these packages were things we'd find that if you go to install other software, they'd all be dependencies. So we kind of figured out, what was the common set of dependencies across all the software we're trying to install. Let's shove it all in one base image so we don't have to re-download that every time. And then we split off, and like I said before, we've got an Oracle image. So we run Oracle JDK and OpenJDK, so we've got an image for each of those. All our applications are based on top of the OpenJDK stack. And then Cassandra and DataStax Enterprise are then based on top of the Oracle JDK. And so yeah, you can see there that they're all based off the Oracle one. and I've also sort of listed the sizes of those images, so you can sort of see how they're kind of kept nice and small. And if you were just to install Apache Cassandra, for example, the one at the very bottom right there, it would end up installing the Debian image, which is 120 meg, plus the common thing, which is another 100 megabytes, the Oracle runtime, which is 300 megabytes, and Cassandra, which is another 300 meg. But if you were then to install DataStax Enterprise, it's already got all those other things. So it would only install the DSE image, which is 40 meg. So it's kind of, you're not re-downloading everything every time, which saves on bandwidth. That can be quite expensive sometimes. We host all our images on this provider called key.io, which is a Docker registry that's got sort of private repositories and things. While they're hosted in Amazon, so downloads of images to Azure is kind of more expensive. So trying to sort of minimize this stuff is quite useful. So combining those two things together, Docker and CoreOS, what does it give us? Docker gives us the immutable images for all our software, which is fantastic. We don't have to do instance replacements if we want to do reinstalls, if we kind of want to get that immutability. And what I mean by that is, I was saying before that we'd do an apt-get install, an in-place reinstall over the top of the existing installed software. If you wanted to kind of do a completely immutable environment every time, the only way that you could do that is to actually create a brand new instance with a new image and start that up. And so that's kind of a slow, it's a very time-consuming process, and things can go wrong, and you lose all the data stored on the instance and all that kind of stuff. So it's just not fun. We wanted to move away from that. And then CoreOS handles the rest. It handles all the OS level updates, the Docker updates, kernel updates, via that in-place update mechanism I was telling you about before. Docker itself is completely provider agnostic, so we run on all the big cloud providers available, including Azure, and those Docker images that we build run across all of them. And then CoreOS also runs on all these major cloud providers, so we've got ourselves a provider agnostic system of images that we can run. We don't have to worry about that. And CoreOS itself, because it is a Linux-based OS, you can of course run it on bare metal servers, which is something that we're sort of thinking about in the future of, for like on-premise installations and things like that. Yeah, so the result is that Instacluster Managed Cassandra can actually run anywhere, which is really cool. And the process for doing that for us is nice and simple. So just getting into a little bit more about how we use Docker to handle versioning of Cassandra, because we're a managed hosting provider of Cassandra, we want to provide our customers a large number of options around what versions that they'd like to run, because they all are slightly different. The newer versions are known for having their bugs. The older versions have less features. So some people, will choose to stick to an older, more stable version of the software that they know and love. And other people are willing to try the latest and greatest and see what happens. So we want to facilitate that. We want to support it. So Docker allows us to do this quite easily. So what we do is we have one Docker image per Cassandra distribution. So there's the Apache version and the DataStax Enterprise version. And then we tag that image with the version number of Cassandra that we're running. So we'll end up with, there's like the Apache image will have the 2.0, the 2.1, and the 2.2 kind of version things that you can then run on your machines. If you want to compare that to the old model of installing Cassandra via apt-get on a Ubuntu machine, or image, sorry, you have to kind of do a separate image per distribution of so you'd have a DataStax image, you'd also have a Apache image. And then you multiply that by the number of versions of all those you want to support. And then depending on provider and all that sort of stuff, you also might have to include region into that. We currently support the two distributions of Cassandra. Amongst them, this is a little bit out of date, sorry, but there was 13 versions at one point that we supported. Between them on 3 cloud providers, of which you'd have to build an image for each one of them, with a total of 29 regions globally, that's 377 images that you've got to manage, and it just grows at an alarming rate. It's like, how do you handle this? If something's gone wrong with a particular thing, you've got to go back and rebuild all this stuff. It's slow, it's time consuming. We just looked at it and went, we need something better. And so that's where Docker comes into play. That's the greatest thing that we use it for. So, like I said, every cluster that people create has a specific version associated with it. People can choose that at launch time. And we wanted to ensure that when people add new nodes to their cluster to expand capacity, or we have to replace a node because the underlying VMs, something's gone wrong with it, or something's been corrupted on the operating system, or there's a number of reasons for that, or they want to even upgrade to larger instances. They want more disk capacity, they want more CPU, something like that. We need to make sure that that machine gets replaced with the exact same version of Cassandra. And the apt-get mechanism, the traditional way, if you didn't have an image for the version that people were running for, say you kind of went, let's just keep kind of the base level and we'll upgrade everybody, it starts getting very difficult to kind of manage these configurations. Whereas with Docker, because you've got all these tagged images, you can just say, install this particular version, and you're off and running. So the end result is that we've got a known, same configuration on every node in every cluster. We know what's going on. We can kind of look at our central database and trust that that's what's running on the nodes. And we check that occasionally, and sure enough, it's all correct. We don't have things that have upgraded automatically because we've got to turn system updates off or something like that. And it allows us to do controlled upgrades. And then if something goes wrong, we can also roll back. So because they're immutable images, you get a clean install of Cassandra every time. It's not this in-place update kind of way of doing things. And it prevents what I call here the diverging systems problem. And that's the issue where, say you start with a base image, and then you install a new version of that software on top of it, and so on and so forth. But then if you build a fresh new image, and as a matter of fact, I've got a picture, I should show you this because that makes it a little bit easier to explain. So on the right-hand side, you can see there that we start off in the green with Ubuntu, and we install a particular version of Cassandra. And then that instance that's running that image, if you want to then upgrade to a new version of Cassandra, you install the new version over the top. But then it's going to be slightly different than if you started with a fresh version of Ubuntu and installed that version of Cassandra on top of it. And then, so you can sort of see there that over time, all the ones that started on the green, they've kind of gone off on their own thing. And then all the ones that are on the blue, they've also gone off on their own trajectory, and so on. And so you kind of end up with this collection of machines that's not quite running what you want it to be running. And it starts becoming quite difficult to manage. So contrast that with the Docker way of doing things, where every time you run a new image on the machine, you start up a new container, you get that thing. And you don't do in-place upgrades, you run a new image. And so you have that nice, clean, single ancestry of things that are running there. And so this kind of lets us do a very controlled upgrade rollout kind of process. So how do we do an upgrade of our nodes? What we'll do is, it starts off with, we build the Docker image for that particular version of Cassandra. We'll deploy this to our testing environments, internally and stuff like that. We'll perform like a clean install. So we go, we want to run this image without there having ever been another instance of Cassandra, another container of Cassandra running on that machine before. And then we'll also try replacing a container with a new version of Cassandra to also verify that that works. And I'll get into that in just a second of why we have to do that. We then enable this version in production for select customers for sort of a bit of field testing and stuff like that. They're like, hey, we want to try out that new thing. It's fixed a bug that we're coming up against. Can you guys make this available to us? So we'll roll that out. And then once we're happy with that version, we can then make it generally available for people. New clusters that people create will run this version by default, and then over time we'll liaise with our existing customers and perform a rolling cluster-wide rollout of this new version. So I said before, why do we have to do testing clean installs versus rolling updates? I thought I had a slide that explained this, but maybe not. Which is, the reason for that is containers themselves are immutable, but something like Cassandra, you go, well, it's a database, it's storing data. Where does that data get stored? If you store it inside the container, if you delete the container, all the data that you've stored in it goes bye-bye along with the container. So where do you put the data so that this process doesn't happen? And Docker lets you do what's called like a bind mount from the host, which is you can mount a directory from the host into the container. And so that then becomes more of a persistence data store for the applications running inside the container. So we do that for Cassandra. The data directory for Cassandra lives on the host on a RAID kind of file system. And it means that if you replace the container or upgrade to a new version, that new version of of Cassandra will have access to the data that the previous version was writing to disk. And so we have to, that's the only thing that hangs around. And so we still do need to test, the clean install thing, i.e. there was never a version of Cassandra running on the machine versus actually upgrading a version of Cassandra to a new one by replacing the container, just to verify that there's no glitches in that system. But that's just the data of Cassandra itself, and rather than the entire operating configuration, operating system configuration, and all the other stuff that can possibly be left behind for like if you do a traditional install over the top kind of mechanism. So I mentioned before that we, CoreOS has this thing called systemd, and we use it for managing a lot of stuff. So systemd is a service management framework. It's a replacement for init, which is the traditional kind of Linux startup boot system. It starts services at runtime and reacts to certain events and stuff. Systemd does the same thing. It's just a little bit more modern. It does things a little bit better than sysv init does. It's got a powerful service dependency kind of system, so that you can sort of say that service A depends on service B. If you start service A, B starts up as well. All the stuff you'd expect for something like this. But one of the cool things that you can do is it's controllable by this thing called dbus, which, as I mentioned before as well, dbus is a inter-process communication mechanism. So it allows you to control systemd from another process. And systemd's got like a little utility. It's a command line thing that you can run called system control, which is the way that you interact with systemd. You can start services with it, stop them, restart them, all that sort of thing. System control, in fact, actually talks to systemd via dbus. So what does that mean? It means that anything that system control does, you can actually do in your own application if you've got access to dbus as well. And why is this important? It means that we don't actually have to deal with shelling out to run commands and all that kind of stuff. We can actually control the whole the whole systemd thing via our Java applications, these management applications that we run and install on the machine. Dbus itself it's socket-based, which is quite useful. Under Linux and Unix, there's this, like sockets, traditionally they're TCP, but you've also got these like file-based sockets, which is, there's a file in the file system that you can open and then you can read and write from it, and other applications can be listening on the other end, and you've kind of got this communication mechanism happening. Dbus uses these file-based sockets, and because they're files, they can be mounted into a container via that mount mechanism that I was talking about earlier. So if you want to control the host systemd stuff from within inside a container, all you actually have to do is mount the dbus socket inside the container, and then it's got access to the host dbus. Therefore, it's got access to the host systemd, which means that you can do things, this is especially useful for CoreOS when, like I said before, it doesn't really have much user land. You're not really supposed to install things on the host. You're supposed to run things inside the container. And then you've got the problem of, if you have to run things inside a container, how do you run a container in the first place? Like, you've kind of got this bootstrap chicken and egg kind of scenario going on, And so what we do is we dump a single service on the machine at startup via there's like a cloud init mechanism as well. That then spawns a Docker container, and then that container talks to the host systemd to then kind of kick off the rest of the process. And why is it so convoluted? It turns out the cloud init on some providers is limited to about I think it's a kilobyte or something. So you can't put much in there. You've got to put all the rest of your stuff somewhere else that you can host larger quantities of information. So Docker kind of works very well for that. So if you have something that just kicks off a container, then that container then bootstraps the rest of the system. This is how you do it. Dbus itself also has multiple language bindings. So you can control Dbus via Python, Java, probably Ruby and all that kind of stuff, which means that it's quite easy to control systemd from your language of choice. So there's an example actually of how you what the Java bindings let you do. The traditional command that you type in to restart, say, the Cassandra service on a machine would be system control restart Cassandra. You can do exactly the same thing through Java via the call to systemd manager restart unit Cassandra. And they are in fact exactly the same thing, because system control itself just uses dbus to control systemd. So they are identical, which means that we don't actually have to shell out, like I say here, you don't have to fork and exec a new process to just launch system control to tell it to do things. You can actually just run it inside your application. So integrating all these things together a little bit more, how do we run Cassandra on Docker? And how do we integrate it a little bit better with systemd? We chose the one process per container model for Docker. Now there is a little bit of debate in the community around do you run single processes in containers? Are they more a process sandbox kind of thing, or are they more a sort of lightweight virtual machine where you've got a whole init system like systemd running inside that container that then spawns multiple processes? Some people go to the extent of even running like SSH inside a container. So you've got like this little mini isolated operating system that runs a whole bunch of background services as well. We picked the first one, which is just the single process per container model. And that basically means that Cassandra runs as process one inside the container. And that, there's actually a few little gotchas that I'll go into a little bit more in a minute around running things as process one inside containers. But it does mean that they are extremely lightweight. You're not running the whole user land, the init system and logging frameworks and all that kind of stuff. That's all on the host. The only thing running in the container is the process that you're interested in. And so in order to do that, we run Cassandra because it's traditionally sort of a daemon style thing. You launch it and it's running in the background. It's got a little switch when you run it, which is foreground mode, which doesn't daemonize the process. So it's running in the foreground. It then responds to sigterm as a normal process would. So the end result is that things like Docker stop and system control stop and all those sort of things will sigterm Cassandra, and then the whole thing shuts down. And like I mentioned before, the Cassandra data and its configuration is persistent on the host. So it means that survives a container restart, or an upgrade or something like that. So there's the example of the Docker run command that we'd use. The data partition contains the etc directory for Cassandra where its configuration file is. That's then mounted into the container under etc Cassandra. And then the data directory for Cassandra would be the same. So we also do something a little bit different, which is and so this is more of a core OS recommendation, which seems to be a little bit at odds with the way Docker works. So there's kind of a little bit of fighting here, but it does work if you know what you're doing. Which is we run Docker containers and we control them via systemd services. So we don't typically call Docker start, Docker stop, Docker run directly. We actually call those from systemd services. So you'd actually go system control start Cassandra, which behind the scenes does a Docker run Cassandra image with all the parameters and whatever else. And then if you do system control stop, it will ask Docker to stop that container, but we've kind of got the service management framework with all its dependencies, systemd, controlling Docker containers so that we can kind of handle, because Docker doesn't really have a sort of very good dependency management thing between containers. You know, if you want to run two, you can link them together, but you can't really say, if you start this, you should also start this guy, and so on. I mean, I think it's on the roadmap. It might even be in the latest version. I don't know. We're kind of, we're not on the bleeding edge of some of this stuff. And what that also means is that because we're running these as systemd services, any log messages printed or anything printed to standard out and standard error gets captured by systemd and then written to this thing called the journal, which is a replacement for syslog and log files on the disk and stuff like that. It's more of a, it's like a database. So it is a structured binary data format for logs, which some people have complained about, but it does mean that you can search it and you can store kind of, enriched metadata about logging events and stuff like that. It's not just, plain text format that's, could be different per application, all that sort of thing. So because we're running Cassandra in the foreground, it prints its log messages to standard out. Then Docker captures those and then forwards them onto systemd, which forwards them onto the journal, and that's how they get persisted to disk. So it is kind of this complex flow of data, but it does mean that everything ends up in one spot. So not only the Cassandra logs, but the host logs, and all the other services that we run in Docker as well, all end up in the journal, which we can then ship off to some other service to do log file analysis and all that sort of thing. And like I said, so if you want to query the journal, you can just run like journal control to access that stuff because it's all in one location. So next up, there's just a few things around some of the tips and perhaps a few small gotchas that we've come up against when running Docker in production. So the first one is process ID 1, and I said I'd come back to this, which is because we're running Cassandra as a single process, there's no like an it framework inside the container. It runs as process ID 1, and process ID 1 gets special treatment from the kernel. Because traditionally, PID1 was a NIT. It's the thing that gets started as soon as the system boots. And so there's a few things that have to happen a little bit differently to every other process on the system, just by nature of, it's this kind of a historical thing. But this limitation, or whatever you want to call it, exists not only on the host, but for every container that's launched as well. So because like process IDs get reset when you start a container, so the first process inside a container will also be PID1, the kernel goes, oh, that's process ID 1, it should get special treatment. It doesn't notice that it's inside a container, it just applies that logic. What is this special treatment? So traditionally processes, they get a signal handler installed on startup. A signal handler does things that like responds to sigterm and all the interrupts and stuff that you can send to a process. PID1 does not get this default signal handler. And that can pose a little bit of a problem for, when you go to Dockerize an application for the first time, it doesn't seem to behave quite right. You kind of go, oh, why if I send it sigterm, does it not seem to shut down? It just goes, continues on its merry way without, even noticing that it's been asked to terminate. And that's because it's running as PID1. And so PID1 will ignore all signals that are sent to it for which the process hasn't explicitly registered a signal handler. So the default goes, oh, sigterm, I should exit, but PID1 doesn't get that default. So if the process doesn't install its own, oh, sigterm, I should exit handler, it just won't do anything on sigterm. And we noticed this the first time we were trying to Dockerize a few applications that would run as things that didn't install these custom handlers. And yeah, you go to stop the container and they just wouldn't shut down. It's like, why is this not working? And then reading into it a little bit more, this is the reason. So it turns out that, and why, sorry, is this a bit of an issue? It's because like Docker stop will send a sigterm to your process first. Then it will wait a little bit, and if it doesn't hear from the process or the process doesn't look like it's shutting down, it hasn't responded to this event, it just goes nuke. It just kills it outright. It sends sigkill, which is completely uncatchable. You can't do anything with it. And that's really bad. You shouldn't be just killing processes randomly because they never have a chance to clean up. You know, something like Cassandra, if you kill it, it flushes all the caches to disk, all the in-memory data, makes sure it's all persistent. Whereas if you just kill it, kill -9, it doesn't have a chance to do that. It's just killed. So this is a very bad thing, and you've got to look out for it. So, like I said, it only affects processes that don't install their own custom handler for this stuff. Bash doesn't by default. So if you've got an application that uses a shell script to launch, and that shell script doesn't do a exec which replaces bash with the process, it kind of spawns as a child, bash will not respond, it keeps running as PID1, it will not respond to sigterm, and then the process that it spawns will also not respond to sigterm, so it all kind of just doesn't work. Whereas things like Java and Python, because they've kind of got this memory managed environment and they need to do a few things at kind of shutdown, they install their own custom sigterm handlers. So out of the box, Java applications like Cassandra will run without any problem. You can run them as PID1, you can send sigterm to the application, or you can stop the container and it will all shut down gracefully, which it works quite well. Another thing that we had to look into was streamlining the apt-get process for installing software in containers. So as part of the build process for these containers, we still do apt-get install Cassandra from a repository, but we only do that once. If we want to do it again, we create a new image. But what apt-get does is it caches the source lists of all the packages, where does it get things from, and it's really recommended not to embed these in your images. It contributes to the size of the image. They can actually be quite large. Some of these repositories have thousands of things. It'll download 50 megabytes or something like that. And what can also happen is that if you're building one of these, if you can think back to that slide where we had that tree of images that all depend on each other, if you're building something like that and you manage to embed the apt-get source list in one of the images at the very top, if you then go to build a new version of one of these child images, it will try and use that cached data, which now might be stale. Because say you only rebuild your base image every, call it every month, but then there's new packages released. That base image will contain stale cache data about what packages are available. And so you do an apt-get install in one of these child images and it goes, the package doesn't exist anymore, what's going on? So you've got to do an apt-get update and refresh all the information. So it's a good idea just not to embed this stuff into your images in the first place. So how do you do that? You actually have to run like a RM over a directory to clean some of this stuff up. We wrapped it up in a script. We called it Docker apt-get install, or DAGI for short, which is basically a wrapper for apt-get install. But it will then do it does an explicit apt-get update to download that list of packages. It then installs the software using a bunch of other options that Docker recommends to do software installations for apt-get as well. Non-interactive, make sure you don't install stuff that you don't actually need, the recommended packages, all that sort of thing. And then once it's done installing everything, remove this cached data so that then the next time you run this script, it has to do the fetch the package list again, which means things are a little bit slower, but you'll never end up in a situation where builds just start failing randomly. Some of the limitations that we've come up against with Docker, which I believe they know about, and they're trying to improve this stuff all the time. Docker is a very fast-moving project. They have new versions all the time. The first one is that when you type into the console Docker run, that actually just is a proxy for the Docker daemon. So that Docker actually runs as two things. You've got this daemon process running all the time. And that's where all the containers are actually launched inside, or they're run as sub-processes of that daemon process. And Docker run actually just proxies sort of data between your kind of current login session to that daemon. This is actually a problem for certain things coming back to like systemd and whatever, where because our systemd services call Docker run, systemd thinks that Docker run is actually the process that you're starting, because traditionally, you go systemd service would start, Cassandra directly, not inside a container, it just started directly. And so it would assume that that process that it's starting can then do things like do watchdog timers and notifications and all these other things. It expects those notifications to come from that started process. You know, there's no point in some other process in the system saying, yeah, I'm alive, pretending to be Cassandra. It wants Cassandra itself to say, yes, I'm alive. It becomes a problem when Docker run isn't actually Cassandra. Cassandra is running under this daemon process, and you can't integrate those things. There's no way to do this tighter integration between these services. The other limitation of running everything under the Docker daemon as a single thing is that if the daemon crashes, everything is gone. They're not run as separate processes. They're all run as children of the Docker daemon itself. So if you kill that, or if it crashes or whatever, you lose all your containers. And that wouldn't be such a problem, I guess, except for because Docker integrates everything into the daemon, like everything, and I mean everything. You run images, you push images up to a remote repository, you pull them, you build a new image. It's all run as part of this daemon process. So if anything in that, one of those things goes wrong, you lose everything else running on the machine. The other thing this means is that because the daemon runs as root because it needs access to a bunch of system services, everything that you do with Docker, including pushing images up to the internet and downloading things from the internet, is also run as root, which could be considered to be a little bit of a security risk. The project hasn't released a sort of official statement about what they think is a good solution to that. But some of the things, like pulling and pushing images, should probably be done not via the root daemon, just for security reasons. The other thing that we found was that Docker's default networking that comes out of the box is really, really slow. On the order of 40% or something like that. And that's when the applications running inside the container get their own network stack, and then you kind of do, you expose ports from within inside the container to the host, and then you can link things together and all that kind of stuff. We avoid this completely by just running with host-based networking, which is that the network stack from the host is the same as what's running in the container, so they're just sort of shared. And that gets around a bunch of other problems as well. The biggest one is this thing called double network address translation. Docker's default bridge networking is actually NAT itself, so you've kind of got, each container gets its own private IP address on a Docker network, and then certain ports are forwarded into that network to specific, hosts, containers. But if you're running on a cloud provider that also does NAT-based networking, you've then got a public address for the machine, a private address for your host, and then that's then the public address for the containers, and then they've all got their own private address as well. So you kind of got to do double port forwarding or whatever else, and that is actually a really painful thing to work around with Cassandra in particular. It doesn't really handle NAT-based networking particularly well. And trying to do it as a double NAT situation is just mind-bogglingly complex. And so we gave up and went, we'll just use host-based networking to keep it simple. We also found that another union file system performance, which what Docker uses that for its kind of layering of things. I won't go into too much about how all that works, but the performance of that is extremely slow. So it basically means that the file system that the processes inside the container see is actually very slow at doing reads and writes. Especially if you're using a lot of small files, which is what Cassandra uses. And so that is another reason to bind mount a directory from the host on a performant file system such as ext4 or XFS or something like that, and mount that into the container and stick anything that needs a performant file system on that. Because the bind mounting into a container is basically, there's no performance loss at all. It's a completely one-for-one kind of thing. So, like I said, we put Cassandra's data directory on this file system so that we can get those performance benefits. And the last thing that kind of bit us a little bit when we started this, why it's relevant to Docker is because it can be used by Docker, is this file system called Btrfs or BTRFS. For a while, CoreOS, like the earlier versions of CoreOS, used Btrfs as its default file system. Now, Btrfs on the cover is actually really cool. It's I don't know if anyone's heard of ZFS, but Btrfs is kind of similar to ZFS. You know, it's this pool of storage. You know, you can just add disks to it, it grows, and then you can kind of cut file systems out of that, and then you can do snapshotting and restores and all these kind of cool features, and you think, oh, that's great. But it is a little bit slower than things like ext4, and it's also not really stable yet. It's still considered to be kind of beta by the Linux kernel guys, and it does have a bunch of really interesting problems that, because we started running this in production, we kind of came up against and then had these very painful. How do we solve these? Because there's not much information out on the internet either about how some of these problems should be solved. But why CoreOS picked it was because Docker can use Btrfs as one of its storage drivers to handle that image layering stuff that I was just talking about previously, and doing snapshots of images and stuff, because it's all built into the file system. So they went, oh great, we can use the file system rather than having to implement it ourselves. So that's why Btrfs was around, but it's probably a really good idea not to use it. And this is probably one of the best things that we saw is, you're running on the machine, and so this is the output of df, which shows you how much space is available on your disks on the machine. And so you see there that the root file system, which is Btrfs, apparently has 3.1 gigabytes available. You then go to create a file, and it goes, there's no space left on the disk. Why? And it turns out that there's some internal stuff in Btrfs that, if you don't do repair operations occasionally, or things can get a little bit out of sync, that suddenly some of these statistics about what the file system reports to the end user are actually different from what it thinks internally. And that just kind of starts to play havoc with a bunch of things. And we saw this in production where, things we're trying to write stuff to the disk, and then we're like, it's not full. Why is that failing? And you have to scratch your head a little bit. And sure enough, there's other people on the net that have seen this, and and eventually we just went, there's too many of these things to deal with. We're just going to switch over to ext4 for storage. And CoreOS must have seen they had enough people complaining about it that they did too. So the newer versions of CoreOS are just back on ext4 as the default file system. Anyway, that's pretty much it from me. So anybody got any questions that we can maybe answer after all?
Maybe. And while you're thinking of questions, don't forget you still get a chance to submit your evals and win some prizes and all that sort of stuff. Over here. Yep.
Okay, so you mentioned that you could have a VM, multiple VMs hosting multiple containers. Is there a way that you would partition the containers and which VMs are hosted? As in, would you have a VM dedicated to, say, containers for database application, and another VM with containers only for the API?
So for I/O performance in the host, for example, things like that?
Probably it depends on your use case. Yeah, you could do, you put your database on one machine and then your application all on the other. But like as to just give you an example, for our central servers, we run Postgres, which is a relational database system for storing all our kind of account data and everything. Because that's all fairly underutilized, we actually run Postgres and our website and our API endpoint, all that kind of stuff. It's all clustered and distributed for uptime and availability. But we run all those, they're all in containers, but we run a copy of each on every machine. But if we suddenly started needing better DB performance, we could probably go, let's run a bunch of dedicated database machines and then run the database container and maybe some other, like a backup agent or something running alongside it as another container.
Other questions?
Anybody else?
Excellent. All right, well, guess what? We've made it to the end.
Woo-hoo.
Woohoo! All right, lunch is on. Go feed up. LockNote will be on soon. Thank you very much for attending, guys. We really appreciate it. And I would say enjoy the rest of Ignite, but we're almost done. So that's it. Talk to you later.
Thank you.
Friends I found, friends